Welcome to the stream, everyone. This is your hacker Lexical Cyan. Hello. Welcome, Rafael. Welcome, Oguzan Polad. Welcome, Yufan. Welcome, Simone Romano. Welcome, Arya Bak. Welcome, Mr. Lucas 265. 欢迎比喵，快点睡觉！为什么还没有睡觉 ？Saint Chris, welcome. 刺猬 welcome. Welcome, Sergey. Welcome, Lloyd. Welcome, Ihato. Programming sucks on. What color is it? Is it the one that's stripped? Everybody should get their programming sucks. Welcome underscore. Welcome Wixie. Welcome Ben. Welcome Ben Satanki. We have two Bens. Rasmax, welcome. You understand better how Pop OS be? How will Pop OS be? Let's see if we can get to that level. It's going to be the Rust language. Welcome Otto. Welcome Rasmax. Welcome Dar, welcome Nettie, welcome Dennis, welcome Sanitas, welcome Drago3X, welcome Azzy8, welcome Batomi. My favorite background noise, glad to serve you. Welcome Konomi, welcome XBoBoX333. Hello. Hello. Today, we're learning the chapter 4 of the Rust book. Understanding ownership, which is Rust's most unique feature. I don't know much about it. I know it's about stack and heap. I'm just going to use my bare minimum knowledge to see if we can conquer the concept of together. Any one of you know Rust? I know underscore knows Rust. I know a lot of people were helping me last time. Welcome Jesus, welcome Roscoe. So what is this ownership? I heard it's about memory, borrowing slices. Every time it comes to memory and pointers, it gets a little trickier. And that's why we will be having the fun. Welcome, Hafnia, 晚上好. It's the hardest chapter. Okay, let's just try to get this done. Let's try to get this done with my cat. My cat is here. Hello, you wanna learn Rust as well? Are you going to be a Rust programmer that makes a new OS? For everybody. Is it buffering? Man! I saw the internet is gonna be okay. Sorry. It's buffering! Man, I don't know what to do. Teaching crabs to read, that would be great. Why is it buffering so badly? It goes every few seconds. That's sad! That's sad. Yo Paul, welcome. Anyways, let's hope the recording is gonna be good. If anything that doesn't go well, I'll still be uploading the recording that's gonna be watchable. There's nothing that can stop me from learning Rust. Okay, let's go. Understanding ownership. Ownership is Rust's most unique feature and has deep implications for the rest of the language. It enables Rust to make memory safety guarantees without needing a garbage collector. So it doesn't have a garbage collector, unlike Java. It's more flexible then. It's important to understand how ownership works. In this chapter, we'll talk about ownership as well as several related features, borrowing, slices, and how Rust lays data out in memory. Let's go! Neko versus Rust. Okay, so what is ownership? Ownership is the set of rules that governs how Rust program manages memory. So it's a set of rules. All programs have to manage the way they use a computer's memory while running. Some languages have garbage collection that constantly looks for no longer used memory as the program runs. In other languages, the programmer must explicitly allocate and free the memory. Rust uses a third approach. Memory is managed through a system of ownership with a set of rules that the compiler checks. If any of the rules are violated, the program won't compile. None of the features of the ownership will slow down your program while it's running. So it doesn't slow you down, unlike some language that has garbage collection. And it's less error-prone compared to languages like C++ that explicitly allocate memory. Rust is using a third approach, memory management. Memory ownership. Because ownership is a new concept for many programmers, it does take some time to get used to. The good news is that the more experience you become with Rust and the rules of the ownership system, the easier you'll find it to naturally develop code that's safe and efficient. Keep at it. Let's keep at it. Hey. Welcome, Matt. When you understand ownership, you'll have a solid foundation for understanding the features that make Rust unique. In this chapter, you'll learn ownership by working through some examples that focus on very common data structure. Strings. Is string mutable or immutable in Rust? You can achieve C and C++ level performance. That's so cool. It's a bit hard to get my head around. Let's see how hard it is. Haha. The stack and the heap. Many programming languages don't require you to think about the stack and heap very often, but in a system programming language like Rust, whether a value is on stack or a heap affects how the language behaves and why you have to make certain decisions. Parts of the ownership will be described in relation to stack and heap later in this chapter, so here is a brief explanation. Stack and heap, where the variables are stored, right? C++ has smart pointers? Ooh. Both the stack and the heap are part of the memory available to your code at the runtime, but they are structured in different ways. The stack stores values in the order it gets them and removes the value in the opposite order. Oh, the first in last out. The last in first out. Yes, the last in first out is the stack, right? This is referred to the... Yes! I'm right, it's the last in first out. Think of a stack of plates. When you add more plates, you put them on the top of the pile, and when you need a plate, you take one off the top. Adding or removing plates from the middle or bottom wouldn't work as well. Adding data is called pushing onto stack, and removing data is called popping off the stack. And all data stored on stack must have a known fixed size. Oh, so you need a fixed size of data to be stored into a stack. Data with an unknown size at compile time or a size that might change must be stored on heap instead. So memory with known size will be put onto the stack. But memory... Wait, not memory, data. But data is in the memory, right? Anyways, data with unknown size will be stored in stack, and data with known size will be stored in heap. Heap is less organized. When you put data on the heap, you request a certain amount of space. Ooh, okay, so it's like... You get some space. You require some space from the heap when you put data in. The memory allocator finds an empty spot on the heap that's big enough, marks it as being in use, and returns a pointer, which is the address of that location. Is that the starting location? The process is called allocating on the heap. and sometimes it's abbreviated as just allocating. So allocating is the process of memory allocator finds an empty spot in the heap and returns a pointer that gives you the address of the heap. Pushing values onto stack is not considered allocating, so allocating is only for heap. Because the pointer to the heap is a non-fixed size, you can store the pointer on the stack. But when you want the actual data, you must follow the pointer. Oh, so you store the pointer in the stack, and you store the unknown size variable on the heap. The pointer on the stack will point to the heap which has the actual data. Ooh. You use heap when you have data that has to be dynamically sized. Think of being seated at a restaurant. When you enter, you state the number of people in your group, and the staff finds an empty table that fits everyone and leads you there. If someone in your group comes late, they can ask where you have been seated to find you. Oh, that's a nice example. So you come to the restaurant early, so you are that freaking pointer that will lead everybody else to the same place where you are. Oh, cool. Fun fact, losing a pointer that points to data on a heap is called a memory leak. The program slowly runs out of heap space and eventually crashes. So there's no way to restore those memory allocated on a heap. It just get lost. So that's why that's a memory leak. It just keep going up. Things like strings and vectors on a heap and fixed size arrays are on the stack. So dynamically sized stuff are on a heap, and the fixed size stuff are on the stack, including pointers. Woohoo! Pushing to stack is faster than allocating on a heap because allocator never has to search for a place to store new data. The location is always at the top of the stack. We put everything on the top of the stack. Comparatively, allocating space on heap requires more work because allocator must first find a big enough space to hold data and then perform bookkeeping to prepare for the next allocation. Looks like allocator is very busy. It needs to find a big enough space for all the data to come in and then note that location so when next group come in, it knows like where to start. Very busy allocating. Or allocating like airline or selling the tickets. That's true. Eventually, if they oversell the tickets, some people can't get in. So the airplane will be leaked. Will there be people standing in the airplane? Okay. Accessing data in the heap is slower than accessing data on the stack because you have to follow a pointer to get there. Contemporary processes are faster if they jump around less in memory. Continuing analogy, consider a server at a restaurant taking orders from many tables. It's most efficient to get all the orders at once. At one table. Get all the orders from at one table before moving on to the next table. So in the restaurant, server takes order table by table, taking an order from table A, then an order from table B, and then one from A again, and then one from B again would be much slower process. By the same token, a processor can do its job better if it works on data that's close to other data, rather than further away. Allocating a large amount of space on a heap can also take time. Let me reread this. Accessing the data in the heap is slower than accessing data on the stack. That's true because you need a pointer. And the processor are faster if they jump around less in memory. So it would be nice if a set of data, one data, is put closer together. I feel like there's some rules I have learned in my computer organization. Like the closer the location is, the less time it takes to find the data. When you close a function, the value passed into the function, including potentially pointers to data on the heap. The values pass onto the function and the function's local variables get pushed on the stack. Okay, so we have a function, it get called. The values pass in the function, so the parameters, and the local variables in the functions are pushed into stack. When the function is over, those values get popped off the stack and they are boom, no use. I'm going to do a lot of rereading because it's gonna be hard, I guess. Lots of things are fast to scan in CPU caching. Ooh. Keeping track of what parts of the code are using what data on the heap, minimizing the amount of duplicate data on the heap, and cleaning up unused data on the heap so you don't run out of space are all problems that ownership addresses. So ownership, the concept of ownership, will help keep track of what parts of code are using what data on the heap. And 2, minimize the amount of duplicate data on the heap. And 3, clean up unused data on the heap so you don't run out of space. If you lost your pointer, you won't be able to clean up the unused data. So that's the leak, how the leak is caused. Yes. Welcome, Jemazi! Thank you for watching. Welcome to Nelstar. Once you understand ownership, you won't need to think about the stack and heap very often. But knowing that main purpose of ownership is to manage heap data can help explain why it works the way it does. So the main part of ownership is manage the heap data. I guess it's to make it efficient. There's 3 reasons. Keep track of what part of the code are using what data on the heap. And 2, minimizing the amount of duplicate data on the heap. And 3, cleaning up unused data on the heap so you don't run out of space. Minimize the amount of state you have to deal with. Ownership is strange, but it helps you to not forget to use the pointers. Nice. So you won't have a dangling pointer. Okay, moving on. The 3 rules of ownership. First, let's take a look at ownership rules. Keep these rules in mind as we work through the examples that illustrate them. So we gotta recite them. We're gonna build them into our brain. The first one, each value in Rust has a variable that's called its owner. Oh, so everything that has value will have an owner. That's very kinky. All the values will have an owner. There's no value that doesn't have an owner. Cool. Number 2, there can only be one owner at a time. Oh, so each value must have an owner. And one and only owner. What is this? Monogamy? And 3rd, when the owner gets out of scope, the value will be dropped. So if we have a scope and it has like variables, when we execute a line that's out of the scope, after that scope, all the values will be gone. So pathetic. So value always follows one and only owner, and when owner dies, the value dies. I have so much empathy for the value. Okay, variable scope. Now we are past the basic Rust syntax. We won't include all the function main code in examples, so if you are following along, make sure to put those examples in your main function, okay? As a result, our examples will be more concise, letting us focus on actual details rather than the boilerplate code. Okay, what is this? Run this code? It runs by itself? That's cool. No, you're not allowed to swear. You'll get banned. I'm the only one who are allowed to swear. I'm sorry, it's my channel. Oh yeah, I do the world. Okay, so what is this? Let's have a string. Is that a string? Yeah, it's a string. This is a immutable string that s equals to hello. I don't like the indentation. This looks better. Cool. The variable s refers to a string literal, where the value of the string is hard-coded into the text of our program. The variable is valid from the point at which it's declared until the end of the current scope. Oh, so if we do this, we create another scope like this. So on this line, s is not valid. On this line, s is valid from this point on. And then when we can do stuff, it's all valid. But once out of that really curly braces, we don't have ends anymore. So if we do print line Marco, is it like this? Print line Marco s, it's gonna throw us an arrow. Is that how you do print line? And let's run it. Cargo run. Yeah, it cannot. It doesn't know it has a. It doesn't have. No, it has a s, right? Wait, hold on. If I do this, it's not gonna know it has an s, right? The s is not found in the scope because it died after this scope is over. It's hard to talk about C++ without swearing. Come on, step. Keep it inside. What is a gosh darn hack? Why are people talking about? There are two string types in Rust, string and string, str and string. Str is allocated on the stack because you know the size. Oh. Wow, okay. And the big string is the one that allocated on Heap. There's so many strings. I hate C++ compilers. All the error messages were giving me such a pain. There are 8 types of strings? No way. I wanna know how many types of strings. How many types of strings are in Rust? There are 2 types. There are 2 types. There are only 2 types. The big S string and the str. String on the heap. Type that? I put the S in the bracket. I don't think it'll work because S is out of scope. Like put that. This is just going to print out exactly this. What? It's not found. Oh wait. Oh wait. It doesn't exactly print out this. I was wrong. It says it's not found in the scope. It's actually trying to print S, but S is not in the scope. So if I remove the scope, does it work? Does it work? If I remove the scope, does it work? does work. It does work. Oh, okay. I don't know. You can just directly put the variable in the curly braces. Nice. Thank you, Atom. Okay, that was fun. In other words, there are two important points in time here. When S comes into scope, it's valid. It remains valid until it goes out of scope. At this point, the relationship between scopes and when variables are valid is similar to what in other programming languages. Now, we are built on the top of this understanding by introducing the string type. The big string type. Let's go. There's already a string. I was wrong then. How many types of string are you? Maybe there are more. すごい string types. You guys know so much. Oh my god. You guys are walking documentations. The string type. To illustrate the rules of ownership, we need a data type that is more complex than those we covered in data type section of chapter 3. The types covered previously are all a known size, can be stored on stack and pop off stack when their scope is over, and can be quickly and trivially copied to make a new independent instance if another part of the code needs to use the same value in a different scope. But we want to look at the data that is stored on Heap and explore how Rust knows when we want to clean up the data. Oh, and the string type is a great example. Cool! And there will be more discussion on chapter 8. We have already seen string literals, where string value is hard-coded into our program. String literals are convenient, but they are unsuitable for every situation in which we want to use text. The string literals are immutable. And another is that not every string value can be known when we write our code. Oh, exactly. So if we want to ask for user input, we need to use a mutable string type, which is a big string. This type manages data allocated on Heap, and as such is able to store an amount of text that is unknown to us at compile time. You can create a string from a string literal using a from function. Oh, you can use a from function? Oh, thank you for donation. Thank you, Dennis. Greenline super chat. Super chat. Thank you, Dennis. Nice one. Oh. Now we are making this a dynamic variable. We make it a type of big string. The double colon operator allows us to namespace this particular from function under the string type rather than using some sort of name like string from. We will discuss this syntax more in the method syntax section of chapter 5, and when we talk about namespacing with modules in path for referring to an item in module 3. Oh, that's a long one. Anyways, this is a double colon operator that introduces the namespace. Is it like the C++ namespace? This is kind of the string that can be mutated. Apparently we can use s.pushString. Oh! It's making a hello world. It's adding a bit more onto the s. So we append the literal after s, and then we print line. Hello, 申老师，欢迎。Okay, so if I run this, cannot borrow as mutable. Oh, okay. So we gotta make this mutable in order to make change on it. And now we have our hello world. Because we can mutate our mutable string. A dynamically typed mutable string. Oi. You can do that. You can declare this type like this. What does the dot into do? Does this work as well? Oh, mute. Oh, it works! It works! すごいね。What does into do? Into Rust. A value to value conversion that consumes the input value, the opposite of from. So you make the string literal into a big string. It's the opposite of from. That's cool. That's cool. Do you guys like to do from or into? Into is a way to explicitly cast things, so must be very convenient. Memory and allocation. In the case of a string literal, we know the contents at the compile time, so the text is hard-coded directly into the final executable. Final executable? So the string literals will be hard-coded directly into the final executable. And the string literals are therefore fast and efficient. But when string is mutable, we can put a blob of memory into a binary for each piece of the text, whose size is unknown at compile time and whose size might change while running the program. So we cannot throw whatever that we put on a heap into the binary. With the string type, in order to support a mutable growable piece of text, we need to allocate the amount of memory on the heap. Unknown at compile time, we hold the contents. This means the memory must be requested from a memory allocator at runtime. We need a way of returning this memory to the allocator when we are done with our string. What does it say? For the string type, we need to allocate an amount of memory unknown at the compile time to hold the contents. And first, we need to request the memory from the memory allocator. And second, we need to find a way of returning the memory to the allocator. When we are done with the string. This is like borrow a book from the library. We need to request the book from the library at the runtime and then return the book back when we are done with it. So the library doesn't run out of books. I have such a nice analogy. The first part is done by us. When we call string column from, its implementation requires memory in it. This is pretty much universal in programming languages. However, the second part is different. In languages with a garbage collector, the garbage collector keeps It keeps track of and cleans up memory that isn't being used anymore, and then we don't need to think about it. In most languages without a garbage collector, it's our responsibility to identify when memory is no longer being used and code to explicitly return it, just as we did to request it. So, without a garbage collector, we need to return the memory when it's not being used. Doing this correctly has historically been a difficult programming program. If we forget, we waste memory. If we do it too early, we'll have an invalid variable. If we do it twice, there's a bug too. We need to pair exactly one allocate with exactly one free. I remember a lock in C. Rust takes a different path. The memory is automatically returned once the variable that owns it goes out of the scope. Here is a version of our scope example from the listing 4-1 using a string instead of a string literal. That looks like the original example I was doing. So S is valid from this point forward, but out of this point is no longer valid, and I think it just returns the memory. Does it do it by itself? Let's see. There is a natural point at which we can return the memory our string needs to the allocator when S goes out of scope. So right here, S goes out of scope and we can return the memory. When a variable goes out of scope, Rust calls a special function for us. This function is called drop. So we don't need to do it. Rust do it. Rust drop the beat. Rust drop it. And it's where the author of string can put the code to return the memory. Rust calls drop automatically at closing curly bracket. So at this point, Rust calls the function drop. And the memory should be returned. The author of the string put the code to return the memory. Is it saying like the person who increment the big string has a function to return the memory? I think so. That person is doing all the memory collector. That person is doing all the work. A nice person. Saves everybody. What's my goal with the Rust? I want to try to go through the entire documentation. And I don't know what to do afterwards. You guys can let me know in Discord. My Discord server as a content recommendation. Is there something fun we can do with Rust? Okay, in C++, this pattern of deallocating resource at the end of an item's lifetime is sometimes called a resource acquisition. It's a new... what is this? Right? Deallocating resources at the end of an item lifetime is resource acquisition is initialization. What does it mean? Resource acquisition is initialization. The drop function in Rust will be familiar to you if you use the RA patterns. Resource acquisition is initialization. It's a programming idiom using several object-oriented statically typed languages. Holding a resource is a class invariant and typed to object lifetime. Resource allocation is done during object creation by the constructor, while the resource deallocation is done during the object destruction by destruct. The struggle of C++. I remember writing a destructor and a constructor. The object lifetime. I was just curious. Where's my book? Where's my book? My book is gone. Oh, he's here. Does Rust support OOP? I would think it does. But it doesn't have class, right? Rust is object-oriented. They have structs and enums. But wait, hold on. Rust isn't object-oriented in data types hierarchy sense, because it doesn't have inheritance. However, because it has both static and dynamic polymorphism, its interface-based implementation hierarchy is object-oriented. Traits is object-oriented. This is confusing. This is like a hybrid. Rust is broke OOP. Structs instead of classes. Oh, I wanna see how that works. Traits are the reinterpretation of interfaces done in Rust and are very elegant. Ooh. Is that a replacement? Hey, I wonder what programming will look like 5 years or 10 years later. You know, like now I feel like Python is so useful, but after, like, say 10 years, will people still use Python? Okay, this pattern has a profound impact on the way Rust code is written. It may seem simple right now, but the behavior of code can be unexpected in more complicated situations when we want to have multiple variables use the data we have allocated on a heap. Oh, so multiple things trying to access the same memory? Let's explore some of the situations now. Is this the NTR situations? Let's go. With variables and data interact, move. What is a move? What is a move? Variables can move? Multiple variables can interact with the same data different ways in Rust. This looks very harmony. It looks like y would equal to 5? Indeed. Now let's look at the string version. What will happen? What will happen? So S1 is a big string. S2, we set S2 equals to S1. But something might be happening inside. But is it like this? No output. Will both S2 and S1 keep its value? So let's see what's happening. This nice graph right here. Take a look at figure 4.1 to see what's happening to the string under the covers. A string is made out of 3 parts, drawn on the left. A pointer to the memory that holds the contents of a string, which is this pointer, points to here. The memory, this is on the heap and this is probably on the stack, right? So a string made out of a pointer, a length variable, and a capacity variable. Hello is 5 letter, so length and capacity is of 5. And on the right are the memories in the heap, and we have pointers pointing at the beginning position. Hello, team. It's not the NTR we know. There's too many NTR happening in coding. It's a messy world. Okay, The length is how much the memory embodies the content of string is currently using. The capacity is total amount of memory embodies a string has received from allocator. The difference between length and the capacity matters, but not in this context. So we can ignore the capacity. When we assign S1 to S2, the string data is copied, meaning we have copied the pointer, the length, and capacity that are on the stack. We do not copy the data on the heap that the pointer points to. In other words, the data representation in memory looks like figure here. So the S2 equals to S1, copy the pointer, the length, the capacity on the stack, but we still point to the same position. Is this what really happened? The representation does not look like figure 4-3, which is what memory would look like if Rust instead copied the heap data as well. If the Rust copied the heap data, it would be like this, but it will be very expensive because we have duplicate data here instead of having a pointer to one piece of memory. Earlier we said that when a variable goes out of scope, Rust automatically calls the drop function and cleans up the heap memory for that variable. But figure 4.2 shows both data pointers point to the same location. This is a problem. When S2 and S1 goes out of scope, they will both try to free the same memory. Oh, that's true. So we set the scope thing. If S1 and S2 are in different scope, and say S1 scope ended, so Rust will go ahead and just remove this heap memory from the heap. But then S2 will be like, where the heck is my stuff? It's gone with S1, but we mean to have S2 to have it like all the time when we copy it. So looks like this is not okay. This is not okay with the memory management. That's called a double free arrow. You can't both be free. And it's one of the memory safety bugs we mentioned previously. Freeing memory twice can lead to memory corruption, which can potentially lead to security vulnerabilities. To ensure memory safety, after the line let S2 equals to S1, Rust consider S1 as no longer valid. Ooh! Its S1 is just gone. Therefore, Rust does not need to free anything when S1 goes out of scope. So S1 is just boom, died. And then S2 like takes over everything. So if we do this, do I try assembly? Not before I try Rust. Okay, let S1 equals to string from hello. And we let S2 equals to S1. And now, if we print one, world! S1 is gonna throw us an arrow because S2 replaced the S1. It prevented from double deleting. What was it? Double free arrow. S2 will have all the pointer, the length, and capacity to S1. But S1 will be gone. Value is moved here. So here, S1 value is moved. It's moved. So it has nothing now. Even welcome. Hello DDSG, welcome. What? The Rust book is the best documentation I've ever found. I'm so glad I'm reading this book. Oh yeah. Okay, so that's like that. If you heard the terms shallow copy and deep copy while working with other language, the concept of copying the pointer length and capacity without copying the data probably sounds like making a shallow copy. But because Rust also invalidates the first variable, instead of calling it shallow copy, it's known as a move. I like simple words. It just move from S1 to S2. Bang! In this example, we will say that S1 was moved to S2. So what actually happens is shown here. S1 gets invalidated, and S2 is from the S1. S1 moved to S2. With only S2 valid when it goes out of scope, it alone will free the memory and we are done. Hey, moving is not shallow copy because the first string is invalid. But I believe that shallow copy doesn't invalidate the first thing. It's called a move. With variables and data interact clone. If we do want to deeply copy the heap data of the string, not just the stack data, we can use a common method called clone. We can discuss method syntax in chapter 5, but because methods are a common feature in many programming languages, you have probably seen them before. Here is an example of the clone method in action. Let me drink some water. Everybody stay hydrated. Alrighty, so to save our baby S1, we can clone it by duplicating the memory in the heap and copying everything from S1 to get our S2. So here, S1 equals to something, S2 equals to something. We're talking about doing an unsafe operation now. Everyone is so pro. Everyone is so pro. Okay, so now it should give us 2 hello. Yeah, works. Just like you clone a repository. When you see a call to clone, you know that some arbitrary code is being executed, and that code may be expensive. It is a visual indicator that something different is going on. Some arbitrary code is being executed. The heap data does get copied. What do you mean by some arbitrary code is being aggregated? And it does seem expensive. Oh, that's what you guys have been telling me to write the a variable inside the brackets. I'm not going to come back to Python. Thank you. Okay, next one, stack only data copy. There is another wrinkle we haven't talked about yet. This code used integer part of which is showing in listing for 2 works and is valid. Yeah, but this code seems to contradict what we just learned. We don't have to call colon, but X is still valid and wasn't moved to Y because integer is immutable. Wait, is integer immutable? It has a known size. Oh, like 8-bit integer, 32-bit integer, right? The reason is that types such as integer that have a known size at compile time are stored entirely on stack, so copies of the actual values are quick to make. This means there's no reason we would want to prevent X from being valid after we create a variable Y. In other words, there's no difference between deep and shallow copying here, so calling clone wouldn't do anything different from the usual shallow copy, and we can leave it out. So we can just copy. We don't even need to call anything when we have things on stack. Rust has a special annotation called copy trait that we can place on types that are stored on the stack like integers are. If a type implements the copy trait, a variable is still valid after assignment to other variable. Rust won't let us annotate a type with copy if the type or any of its parts have implemented the drop trait. Oh, so when there is a heap allocation, then you won't be able to copy. If the type needs something special to happen when the value goes out of scope, and we add the copy annotation to that type, we'll get a compile time error. So when we define our own type, we need to think about, do we want the copy or do we want the drop? So what types implement the copy trait? You can check the documentation for a given type to be sure, but as a general rule, any group of simple scalar values can implement copy, and nothing that requires allocation or is some form of resource can implement copy. So simple scalar values implement copy. As I said, if there's no job, then you can do copy. Integers, boolean, floating point, character type, tuples. If the content types are all also implement copy. Cool, that's copy. Okay, going on, ownership and functions. The semantics for passing a value to a function are similar to those for assigning a value to variable. Okay? Oh. Passing a value to a function like this. Passing a variable to a function will move or copy, just as assignment does. Listing for 3 has an example with some annotations showing where variables go into and out of scope. Oh, so many annotations. So, we go from the top. S comes into the scope, and now S value moves into the function and is no longer valid here. Oh, so S is the value. Okay, wait. this is a dynamic variable, and the value moves into the function and is no longer valid in this scope, right? And x comes into the scope, and x moves into the function, but because 5 is a 32-digit unsigned integer, so it's a copy instead of passing in the actual value, so we can still use the x forward. And now here, x goes out of scope than s. But because s value was moved, nothing special happens. So this here, it follows the stack sequence. Last in, first out, x goes out of scope, and then we go to s. But because s doesn't have a value, so nothing special happens. And then there's a function of take ownership. It takes some string. That's why the function is take ownership. It takes the value of s and makes it invalid. The sum string comes into the scope, and then we print it, and then some string goes out of scope, and job is called here. The backend memory is freed here. And here makes copy. Integer comes into the scope, and some integer goes out of scope, nothing special happens. Do we not delete the integer? Copy is when it's a stack value and it's implicit. So here, the integer goes out of scope, probably removed from the stack. That's it. If we try to use s after the call to take ownership, if we try to use s after this, it's probably gonna throw an error. Yeah, compile time error. These static checks protect us from mistakes. Try adding code to main that use x and x to see where you can use them and where the ownership rule prevents you from doing so. Welcome, Tropical Fan! Hello! So if I copy the code over, and if I try to print here, it won't let me do it because the ownership has been taken. But if I do it for the x, here, line 11. What am I missing? Oh, shoot! What have I been doing? It should be like this. Haha. I was like, wait, that wasn't supposed to be. Okay, now it's good. Let's try S again. Oh. If I try to print S right here, it's gonna throw me an arrow. Because the arrow was moved here. Yay! Yay! Return values and scope. Returning values can also transfer ownership. Listing 4.4 shows an example of a function that returns some value with similar annotations as those in listing 4.3. What does this say? Let me copy it over. Yeah, I think you can do curly braces with the name of variable. Looks like it's a new feature in the new version of Rust. What? It was added 2 weeks ago? Wow, so new. Okay, what do we have here? So, that S1 equals to gives ownership. What does gives ownership do? Ooh. It gives ownership. Gives ownership will remove its return value into the function. Will move its return value into the function that calls it. Let it return. It returns some string. You don't even need a return keyword. Because this is return, right? So we have something, some string. Value is yours, and it gets returned. And gives ownership will remove its return value. Well, not remove. Will move its return value to the function that calls it. So it will give the value of some string. It will give the ownership of the value to S1. And S2 will be a dynamic hello, dynamic string. And S3 will be takes and gives back S2. What is takes and gives back S2? This function takes a string and returns 1. What? Oh, it doesn't return 1, it returns a string. It takes a string and returns a big string. It just takes the string and returns it. So it takes S2 and returns S2. So now this S2 should be invalid because it's been taken, right? Let's see. So S2 comes to the scope and S2 is moved to takes and gives back, which also moves its return value to S3. So basically it's equivalent of S2 moved to S3. S2 should be invalid, I think. The ownership of a variable follows the same pattern every time. Assigning a value to another variable removes it. So if we assign a value to another variable, then the ownership is removed. When a variable that includes data on the heap goes out of scope, the value will be cleaned by drop unless the ownership of data has been moved to another variable. So when a variable has data on the heap goes out of scope, the value will be cleaning up by drop unless the ownership has been moved to another variable. So if you want the variable to be kept, you need to use something to transfer the ownership. Crypto and web dialog. Oh, so people use Rust to do crypto? A lot of embedded engineer here. What do you guys do? Program chips? Okay, well this works. Taking ownership and returning ownership with every function is a bit tedious. What if we want to let a function use a value but not take ownership? It's quite annoying that anything we pass in also needs to be passed back if we want to use it again. In addition to any data resulting from the body of function that we might want to return as well. So this is saying managing ownership in every function is a bit tedious. There's a situation we just want to use the value, but we do not want to take the ownership. And also, if we pass the ownership in a function, we need to pass back. So, we are learning something new, aren't we? Rust does let us return multiple values using a tuple, as shown in listing 4.5. So we have a main function of S1, and then we have a main function that has a S1 of big string hello, and then we have a tuple of S2 and length equals to calculate length S1. The calculate length S1 returns a tuple of string and usize. It returns the string itself and the size. So Rust does allow us to return multiple values using a tuple. That's very neat. I like it. Returning ownership out of function is a big thing. Ooh. Graphic programming with WGPU. Wow. Graphics programming. It sounds like a lot of metrics. So cool. I use Rust for everything. A lot of features like if statement being expressions are so hard to go back from. Unlikely I'll ever do a serious project in anything else again. Really? Really? Yeah, but if I learn Rust and I find myself can't go back to other languages, what should I do? People is a cousin too. Security, wow. Deep data management. So cool. Okay, returning to this program. Oh, it's gonna talk about references. Join the Rust evangelism strike force like the rest of them. Are we having a revolution here? Oh, the people watching and waiting? Or you guys want to start a revolution? Of bringing Rust to a bigger community? Let elementary students learn Rust instead of Python? Let's go. What is the Rust pandemic? We have had enough pandemics. Okay, let's go to references. Using a value without transferring ownership. References and borrowing. The issue with the tuple code is that we have to return the string to the calling function so we can still use the string after the call to the calculated length. Because the string was moved to calculate length. Instead, we can provide a reference to the string value. A reference is like a pointer in that it is an address we can follow to access data stored at that address that is owned by some other variable. Unlike a pointer, a reference is guaranteed to point to a valid value of a particular type. Wait, hold on. Let me read the original code again. What happened to the reference? Oh, thank you for the donation. Nice support, Sergey. Sergey, thank you so much. Nice support. Have a good night. Thank you for watching. Have a good dream. Okay, what's going on with the ownership here? So we take the S1 and return it to S2. We return it because S1 is gone. We return the S2. I was wondering, like, calculate length doesn't need to return a string, but it returns because we moved S1 into the function and we got to get it out. And this is bad, so we want some reference. Okay, it's making sense. So, with reference, here is how we do it. We put the reference with the ampersand, and we put it into the function. And then we can just do s.length to return a usize. And S1 gets to keep its value. S1 still has the ownership and doesn't need to be in a function and get through all the struggle. That's nice. That's super. Let me translate it. Oh, we got a lot of Russian friends. Hello, thank you, Atom. Nice fun. Okay, going on. First, notice that all the tuples code in a variable declaration and the function return value is gone. Yes, the tuple is gone. Second, note that we pass the reference to S1 into calculated length, and in its definition, we take this type, the reference of the big string, rather than a string. These ampersands represent references, and they allow you to refer to some value without making ownership of it. So if we look at the graph, we have a string, a pointer. A pointer points to the value on the heap. Wait, hold on, no. What is this? This is a pointer, this is the thing on the stack, and this is the heap. I was wrong. So, a pointer S which is this, which is in the function. It points to the S1 pointer, or it's a reference to the pointer of S1 and access the data. Pointer pointing to a pointer. My brain has too many pointers. A diagram of ampersand string S is pointing at the string S1. Note, the opposite of referencing by using ampersand is dereferencing, which is accomplished with the dereference operator star. Is this a star? I say this is a star. We will see some uses of the dereference point operator in Chapter 8 and discuss details of dereferencing in Chapter 15. Let's take a closer look at the function call here. So we have a S1, a big string, and then a length returned from calculate length and a reference of S1. The reference of S1 syntax lets us create a reference that refers to the value of S1 but does not own it. Because it does not own it, the value it points to will not be dropped when the reference stops being used. Likewise, the signature of the function uses ampersand to indicate that the type of the parameter S is a reference. The signature of the function uses this to indicate that the type of parameter S is a reference. Like this, I use this to indicate this is a reference. So, if we look at this, S is a reference to a string. S, it's a reference to a string. And here, S goes out of scope. But because it does not have ownership of what? Ownership of what it refers to. It doesn't have ownership of what it refers to, so nothing happens. Makes sense. The scope in which the variable S is valid is the same as any function parameter scope. But the value pointed to by the reference is not dropped when S stops being used because S doesn't have ownership. So if I don't own you, I can drop you. It's like you cannot divorce a wife if you don't have a wife. Makes sense. Okay. When functions have references as parameter instead of actual values, we won't need to return the values in order to give back the ownership because we never had ownership. We call the action of creating a reference borrowing. This is the infamous or famous borrowing. Famous borrowing. We create a reference to borrow. Oh, we borrow a wife, but we don't own a wife, and we can't drop it. Wait, this is a buy. This is a buy. I'll stop my strange reference. Okay, as in real life, if a person owns something, you can borrow it from them. When you are done, you have to give it back. Oh my god, the wife example is so strong. I feel so ethically challenged. But okay, ignore me. Let's Let's go to code. Ugh. So what happens if we try to modify something we're borrowing? It doesn't work? Why it doesn't work? Let's see. Oh, of course. So we have a big string of hello. And then we want to change. You want to change? You put it into change function. The reference of s. And then you try to edit it here. But it wouldn't work. It wouldn't work because all you have is a reference. It's like you have a photo of other people's wife. You cannot actually touch it. So if we actually run it, yeah, it's the same arrow. It's a reference, so data it refers to cannot be borrowed as immutable. Just as variables are immutable by default, so are references. We are not allowed to modify something we have a reference to, so you can only see it. It's like a read access. With wife. Don't take other people's wife picture without permission? What? That's a thing? Then I should be in jail. I bet. Mutable references. We can fix the code to allow us to modify a borrowed value with just a few small tweaks that use instead immutable references. So, if we use a mutable reference like this, then we will be able to change the content. Does it need to return? Would this work? Need to do this. But it didn't complain about other stuff, did it? So it's supposedly give me a hello world. Oh, cannot borrow as immutable. So how about changing this to a mutable big string? It even tells me how to fix my code. What a nice compiler. This is the best experience I ever have. Yeah, I successfully changed other people's wife. I just need a mutable wife. Hooray! As long as the variable is mutable, we can use the mutable reference to change it. Words of wisdom, desu. Thank you. Thank you guys for debugging. Yoshi. Mutable reference have one big restriction. You can only have one mutable reference to a particular piece of data at a time. This code that attempts to create two mutable references as will fail. So you cannot have two people borrow your wife. So if I do that, S1 equals to a mutable reference of S, it's probably not going to let me do it. I bet it let me do it. Why? Why? Because it was done? You can have 2 people borrow your wife, but not 2 mutable borrows of your wife. Oh. So I can only have 1 mutable borrow, but infinite number of borrows? Of referenced borrow? After call, you're free to multiply reference the variable again. Oh. So after the call is done. So if I do this again, would S1 work? Or just the entire thing just fail? I think the entire thing will fail. Yeah, it wouldn't let you borrow. But how about just one mute borrow? Cannot borrow as immutable because it's also borrowed as mutable. So once it's borrowed as mutable, it cannot happen again. So immutable you can borrow unlimited time, but once you borrow it as mutable, you cannot borrow it as immutable or mutable. You cannot mix mutable and immutable reference to my life. The only one mutable. I should just change S into a wife. Think of mutable as unique, as Rust only allows you to mutate a variable if you have the only reference to it. Oh. But I can only mutable reference it once. One and only. 40. Thank you, everyone. Okay. So the arrow here says we cannot borrow S as mutable for more than one time. The first mutable borrow is in R1 and must last until it's used in print line. But between the creation of that mutable reference and its usage, we try to create another mutable reference in R2 that borrows the same data as R1. So now I have a question. Once I'm done using it, like this. So, I think after I'm done using it, I'll be able to borrow it again. Recycling of waifus? Yay! That worked! Just like how we were originally using the mutable reference in the function. You can have as many people look at your wife at once, but only one can interact with her at a time. And you two need privacy while interacting with your wife, so no one looking while interacting. This is really a buy. This This is another universe. Okay, it doesn't work. It doesn't work on Earth. I'm coming from Neon Star. Maybe in some parallel universe, you can do that. Oh, that was fun. This is my fault. This is not my fault. This is not my fault. This is humanity. The fault is in humanity. This. Okay. Moving on. The restriction preventing multiple mutable references to the same data at the same time allows for mutation, but in a very controlled fashion. It's something that neurotictions struggle with, because most languages let you mutate whenever you would like. The benefit of having this restriction is that Rust can prevent data races at the compile time. A data race is similar to a race condition and happens when these three behaviors occur. Two or more pointers access the same data at the same time. At least one of the pointers is being used to write to the data. There's no mechanism being used to synchronize the access to the data. So it's trying to prevent simultaneous write. Data races are not fun to develop in other languages. So by doing only allowing one mutable reference, it makes it just completely prevent data racing. Data races cause undefined behavior and can be difficult to diagnose and fix when you are trying to track them down at runtime. Rust prevents this problem by refusing to compile code with data races. As always, we can use curly brackets to create a new scope, allowing multiple mutable reference that's not simultaneous ones. Oh, okay. Hi Marcos, welcome! This is just turning into an exercise in how badly we can phrase a borrow checker explanation. You know, the more funny it is, the easier to memorize. We're doing this for the humanity. How to prevent data race, don't run the code. Oh, we need the money! The entire system is here to prevent simultaneous modification of a value from several places, thus ensuring it doesn't suddenly change when you're doing something else with it. That's so cool. A place where nobody races. Nice. Big props to Rust. Big props to Rust. Rust enforces a similar rule for combining mutable and immutable reference. This code would result in an arrow. I like arrows. Show me what's the arrow. The two reference, no problem, but one mutable reference, big problem. Does it have to be a big problem like this? What's the problem? What's your problem, bro? Show me. Immutable borrows occurs here. Mutable borrows occurs here. Cannot compile variables. Cannot borrow s as mutable because it's already also borrowed as immutable. So we also cannot have mutable reference while we have an immutable one to the same value. Users of an immutable reference don't expect the value to suddenly change out from under them. Oh, because we don't they don't want the value suddenly change, so we shouldn't mute them. R3 needs parity. I just cannot see it. Very true. Cannot mutate something that's already been referenced. Russ doesn't like it. It's respect. It's respect. Where am I? Oh, multiple immutable references are allowed because no one who is just reading the data has the ability to affect anybody else reading of the data. Note that the reference scope starts from where it is introduced and continues through the last time that the reference is used. For instance, this code will compile because the last usage of immutable reference, the print line, occurs before the mutable reference is introduced. So as long as we use it, we finish using it, then everything just refreshes and can be compiled. It would be bad if something you were borrowing suddenly changed in front of you. That makes sense. Like if you are borrowing a 3 and suddenly it becomes a 5. So the borrowed wife suddenly changed in front of you, what would you do? That's very yabai. That's no good. I don't want my borrowed wife to change. Rust doesn't like it either, so it's good to have everybody just have this immutable reference to the same wife. So it's like, if you're gonna write something, if you're gonna change your wife, only one person can do it. But if you wanna read a variable or a wife, everybody can do it. Okay, this is yabai. Yabai. The scope doesn't overlap, so this is allowed. Let's run it. Hello and hello and hello. It works. The ability of the compiler to tell a reference is no longer being used at the point before the end of scope is called non-lexical lifetimes. What is a non-lexical? What is a lexical? What is lexical? Relating to words of or vocabulary of a language. Anyways, compiler has the magic to know where is the last time the two variables are used. And show me the right arrows! Yay! Even though boring arrows may be frustrating at times, remember that it's a Rust compiler pointing out a potential bug early and showing you exactly where the problem is. Then you don't have to track down why your data isn't what you thought it was. Nice, so I don't need to consider data erasing. Phew! Thank you, Rust. An example of non-lexical lifetime would be a smiley face. A smiley face? Huh? Wait, why? Are we trying to do this? Oh, it's actually a because This smiley face is not lexical. Is that what we are trying to prove? Oh. Lexical scope is basically the property of variables to be visible within the block of function they're defining. Lexical lifetimes would mean that a reference always stay alive until the end. Oh, so non-lexical means it doesn't stay, the lifetime doesn't stay at the end. Let cat equals to Lamar, let diamond equals to wife? What? So lexical lifetime is the thing that a variable leads the entire program, but non-lexical lifetimes means the variables dies as the program goes. That ice kite, what is it? Is that ice? Look at equals to 5. Okay. Don't worry about it about much later. I think I somehow get it. It's the compiler's ability to tell when a reference is no longer being used. I'm gonna grab some water and come back really quickly. You guys can read off Dangling Reference. Haha. Okay, be right back. What? Wait. Let me grab some stuff. Yo, I'm back. Hello. Are we reading Dangling Reference? Let's read. In languages with pointers, it is easy it erroneously creates a dangling pointer, a pointer that refers to a location in memory that may have been given to somebody else. By freeing some memory while preserving a pointer to that memory. Dangling pointers, I do remember it. A pointer that references a location in memory that had been given to somebody else. By freeing some memory while preserving a pointer to that memory. In Rust, by contrast, the compiler guarantees the reference will never be dangling references. If you have a reference to some data, the compiler will ensure that the data will not go out of scope before the reference to the data does. So Rust doesn't allow dangling reference. I think dangling pointer is when we free out the space, but we forgot to delete the pointer. So it's pointing at the wrong place. Pointer that do not point to a valid object of the appropriate type. But in Rust, we won't have dangling pointers because Rust prevents it. Let's try to create one. So in the main function, let ref to nothing equals to dangle. And in the dangle function dangle, 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 daikazoku. It's a song from anime. Sorry, I'm too weep. Dangle returns a string reference. Yeah. Returns the string reference. S goes out of scope at the end of the dangle. So return the reference of S is an arrow. Let's see the arrow. Let's visualize it. What is going on? Expected missing lifetime specifier. Expected name lifetime parameter. The function's return type contains a borrowed value, but there is no value for it to be borrowed from. The error message refers to a feature we haven't covered yet, lifetimes. We'll discuss lifetimes in detail in Chapter 10, but if you disregard the parts about lifetimes, the message does contain the key to why this code is a problem. This function's return type contains a borrowed value, but there is no value for it to borrow from. So what happens? Here, the dangle returns a reference to a string, And here, S is the new string. And we return a reference to the string S. And here S goes out of the scope. So its memory goes away, danger. So we return a reference to S, but S is gone. So this is a reference to nothing. What Clandid visual novel stream? Will people be interested in that? 欢迎精灵猫猫 Welcome, Gover Joe. Dangle Daikatsu. Oh. Dangle Daikatsu. Dangle. Well, thinking about the story, it is pretty dangle. If you want to return a reference, it has to live longer than the function. Because it only lives as long as the function doesn't match up. So S dies when it's the end of the function. So we cannot return its reference. S will be deallocated here. But we try to return a reference to it. That means the reference will be pointing to an invalid string. That's no good. Rust won't let us do this. So the solution is to return the string directly. So it doesn't die. It lives in reference to nothing. So if I print it, it should show me Anya. Let's see. It shows the Nya! Oh yeah! It shows the Nya. The whole mono. This is returning back. ASDF is actually a reference, but it gives the duration of the entire program. What is ASDF? The rules of references. Let's recap what we have discussed about references. At any given time, you can have either one mutable reference or any number of immutable references. So one mutable reference or any number of immutable references. You cannot mix and match. And the references must always be valid. The two rules about references. One, you can have either one mutable or unlimited immutable references. Two, reference must always be valid. You cannot have dangle. Okay, let's look at slices. The slice type. Slices let you reference a contiguous sequence of elements in a collection rather than the whole collection. A contiguous sequence of elements in a collection rather than a whole collection. Oh, okay. It's like you can slice the string into different parts. A slice is a kind of reference, so it does not have ownership. Okay, I think I cannot use the waifu example here, otherwise it will be inhumane. A slice. Hi. From 4 to 7. Here is a small programming problem. Write a function that takes a string and returns the first word it finds in that string. If the function doesn't find a space in the string, the whole string must be one word, so the entire string will be returned. To write the signature of the function. Function first word. It takes a argument of a string. What does it return? Because the slice is a reference, so does it return a reference of string? The first word function has parameter. We do not want ownership, so this is fun. But what should we return? We don't really have a way to talk about a part of a string. However, we could return the index of the end of the word indicated by a space. So let's try that. Okay. Plan change. What? Planet is a slice of life anime? It's like a sample of our daily life? It is. It's a very nice story. It's like my life favorite anime. As bytes. For I add item. No. Wait, what am I writing? I make the string into bytes. What is this? Bytes.iter is an iterator, and we enumerate the index and the value of the byte. And then if item equals to empty string, empty character space. No, empty character is not a space. If the item equals space, we return the index. That's the size of the first word. The return value of enumerate is a tuple, and you pattern match the tuple into variables. That's like my favorite thing in Python. I like to use enumerate. I like the kind of anime more. I did play the game though. That was a very long time ago. 10 years. Okay, it returns the length of the string. Then what does the I do? Hello. Oh. Wait. So if we find a space, we return line. If we don't find a space, we return the length of the string. Perfect. Because we need to go through the string element by element and check whether our value is a space, we'll convert our string to an array of bytes using the sbytes method. We will convert our string to an array of bytes. So this is the conversion, just like from. Next, we create an iterator over the array of bytes using the iterator method. So we iterate bytes and the enumerate wraps the result of the iterator and returns each element as tuple, which is index and a reference to the element. Because the enumerate method returns a tuple, we can use pattern matching like this. And we use reference item for the single byte in the tuple. Because we get a reference to the element, we will use this. So now the item will be the value. We search for a byte that represents the space using the byte literal syntax. If we find the space, we return the position. Otherwise, we return the length of the word. Yes. Absolutely love it when I use Python. We now have a way to find out the index of the end of the first word in the string, but there's a problem. We are returning a usize on its own, but it's only a meaningful number in the context of a string reference. In other words, because it's a separate value from the string, there is no guarantee that it will still be valid in the future. consider the program in listing that use the first word function in 4.7. What? So it's meaningful when it is a reference to the string. There's no guarantee it will still be valid in the future. Okay, move on. We use an implicit return. We're here. We use Unicode and each character might be more than a byte long. Oh. Ah, stream is buffering. Let's hope we come back. Okay. Let's read this. Let's read this. So we have a hello world and then we pass the hello world in, the reference of the hello world in, and then this empties the string, making it equals to that. The empty world still has the value 5 here, but there's no more string that we could meaningfully use the value 5 with. Word is now totally invalid. Oh. Hello. I think it's back. Sorry for spike. Ooh. Okay, we're coming back, right? I just read this program. It's saying that if s that's initialized here got emptied, then we will have world equals to a number, but there's nothing we can use the number to. So what do we do? This program compiles without any errors and will also do so if we use word after calling s.clear. Because word isn't connected to the state of x at all, word still contains value 5. We could use that 5 with a variable s to try to extract the first word out, but this would be a bug because the contents of s has changed. Having to worry about the index in word getting out of sync with the data in s is tedious and error-prone. Managing these indexes is even more brittle if we write a second word function. Its signature would have to look like this. Oh, it returns the to position. Now we are tracking a start and an end index, and we have even more values that were calculated from data in particular state but untied to their state at all. We have 3 unrelated variables floating around that need to be kept in sync. Luckily, Rust has a solution to this problem: string slices. Oi! I think Go also have it. Like a lot of language have it. My friends read the audiobook then. Then I can really do an audiobook. What is sharp language? My language is very safe. Yeah. It's not exactly children friendly, but I never label myself to be children friendly. Okay, let's look at the string slices. A string slice is a reference to a part of a string, and it looks like this. So S is a string, and let hello equals to 0, 1, 2, 3, 4. So it has the beginning index and the exclude end index. And the world is 0, 1, 2, 3, 4, 5, 6 to 11. Rather than a reference to the entire string, hello is a reference to a portion of the string, specified in the extra 0 to 5 bit. We create slices using a range within brackets by specifying starting index and ending index. The slice data structure stores the starting position and the length of the slice, which corresponds to the ending index minus the starting index. So in the case of let world equals to this. World would be a slice that contains a pointer to the byte at the index 6 of S with a length of value 5. World would be a slice that contains a pointer to the byte. Oh, so world is a pointer, and it's a pointer with a starting position of index 6 of S, and it has a length value of 5. And it's sharp 16 slice. Yay. Thank you for subscribing, Gabber. Welcome to Nelstar. 欢迎 DVD. Hello. A diagram. String slice referring to a part of a string. Oh, so the S hello world, the pointer is at the index 0, it has a length and a capacity of 11. And the world, the slice of world starts from index 6 and it has a length of 5. With Rust, range syntax, if you want to start at index 0, you can drop the value before the two periods. In other words, these are equal. Okay, very nice. You just ignore the 0. By the same token, if your slice includes the last byte of the string, you can drop the trailing number. That means these are equal. What are equal? Oh, we can ignore the ending index. You can also drop the both value to take the slice of entire thing. But why? Why is it naked? See hashtag. It's C#. I'm not a quick learner. I'm not. I did it with some learning in other language and you guys help. Fat pointers. The pointers contain the metadata about their value they're pointing to. What? Is there skinny pointers? Oh, fat pointers contains the metadata. Like the location, the entire thing. The length. Oh, I can see. It has more data. It has like explicit data about some variables. String slice range inlets must occur at valid UTF-8 character boundaries. If you attempt to create a string slice in the middle of a multi-byte character, your program will exit with an error. What? Like 2.5? Oh no, this is the thing that you guys keep mentioning. It needs to be valid if you have 8. If their character that's more than like 1 byte, you can't slice it. It's like slicing through a stone. You cannot do it. You're not tangible. With all the information in hand, let's rewrite first word to return a slice. The type that signifies the string slice is written as reference to. Okay. Oh, so this type is specifically for slice. So here we pass in the reference to keep everything the same besides returning the slice from 0 to I. Oh, and I just return S. No, I need to return the slice type of this. Boom boom. This would be good. Hello, Letty. LED. LED. Okay, bye bye. What is this? Oh, function scenarios. I didn't even use it. What the heck? My brain is going into places. Let's copy something. Oops. Copy the wrong thing. Okay, we have hello world. And then can we print line? Would it print a reference? First word reference of an S. Would this work? No. Gotta put it into its container. Try. No. I'm missing this. Wait. I do it line by line. That world equals to this. And okay, it gets the first hello with a comma. There's a skinny pointer too. Wow, with a sim pointer, the new object type propagates to all places. With a sim pointer, the new object type propagates to all places that have a reference to the project or object. With a that operator is a local operation. I can use the inline syntax. I can only be using variables. Soka. I want it too much. Welcome, Mom. Thank you for subscribing. I do want to know what is a skinny pointer. scheme pointer, the scene pointer, the pointers, scene pointers, fat pointers, alignment, oh my. Okay, I'll find it out later. Welcome, cat. Hello. Okay, where am I? Oh. So, if I clear the S here, it's gonna give an error because the reference is gone, I think. Wait. Oh, let me mute. Immutable borrows occur here. Mutable borrows occur here. Oh, this is... I cannot borrow it. Recall from the borrowing rules. If we have an immutable reference to something, we cannot take mutable reference. Because clear needs to truncate the string. It needs to get a mutable reference. The print line after the call to clear uses the reference in word, so immutable reference must still be active at the point. Rust disallows the mutable reference in clear and the immutable reference in word from existing at the same time, and compilation fails. Not only has Rust made our APIs easier to use, but also eliminated an entire class of error at compile time. Yay! So it doesn't allow it to clear. So easy. It's Cyan using Linux on Mike. I'm using a Linux server. I'm connected to a Linux server. R18 plus, oh god. This is not what you think. This stream is not R18 plus. I'm just using Rust 2018. Oh no. Oh no, I'm gonna get banned for being R18. Yeah, bet. String literals are slices. Recall that we talked about string literals being stored inside a binary. Now we know about slices, we can properly understand string literals. Oh, what? String literals are slices? What? I didn't know that! Oh my god. So, when s equals to hello world, it is actually the type of s. It's the reference that this ampersand str. It's a slice pointing to that specific point of the binary. This is also why string literals are immutable. Ampersand str is an immutable reference. Ooh. So all string literals are ampersand str, which is immutable reference. It points to a specific point of a binary. String slices as parameters. Knowing that you can take slices of literals and string values leads us to one more improvement on the first world, and that is its signature. I thought we were already using it. A more experienced Rustacean will write the signature showing listing 49 instead, because it allows us to use the same function on both big string and small string values. So now we can also, if we use this, then this can be a string literal. Does this needs to be? I don't think you can do that with like. So this would give us the same result. Let's see. It does. It does. So now you're using this small string reference. I can do it on string literals too. So I'm connecting to a Linux server using SSH. But I'm streaming with Windows. We can be R21 plus with the Rust 2021 edition. Yep. I'm forever 18. I can't even stream my own content. It's gonna kick me out. Kondeho, welcome. Hello. Thank you for coming, Sagittarius. Have a nice day. See you next stream. Okay, so we improved the first word function so it can be down on string literal and the slices, and the literals are string slices. Well, everything's a circle. Will Cyan program a linked list in Rust? What? Oh, am I expert of pointers after all this? Dago? Jonathan, thank you for subscribing. Welcome to Nailstar. You guys don't like... Wait, what? Is linked list like a big challenge in Rust? Rust evangelism was strike for. Gosh. The too many linked list book. What the heck? Yeah? I haven't struck yet, guys. I need a struct to do linked list. Are we going to do like double linked list? Go one way and the other? I don't remember anything about linked list. I suck at the code. Okay, continuing on. If we have a string slice, we can pass it directly. If we have a string, we can pass a slice of the string or a reference to the string. This flexibility takes advantage of the deref cohesion. Cohesion. Defining a function to take a string slice instead of a reference to a string makes our API more general and useful, without losing any functionality. Oh yeah! The first word works on slices of string. Partial and whole also works on reference of big string. It works on everything. Hey! Other slices, string slices as you might imagine, are specific to strings, but they are more general slice type too. Consider this array. Okay, this is my favorite. This is an integer array. Just as we might want to refer to a part of a string, we might want to refer to a part of an array. So we can do this. Hey, this is that. Wait, what? 3. 0, 1, 2, 3. So it's just 2 and 3. It's just 2 and 3. Linked list is next to impossible? Why? Why? Implementing the... Oh. I felt implementing anything is like tricky. Doesn't the borrow checker hate a singly linked list with circular reference? Oh. My brain is in a circular reference. My brain is currently dangling. So dangling. Gosh. This slice has type. What is this? So we have an integer array and we slice 2 and 3. And it has the type reference to 32-bit integer. It works the same way as string slices do, by storing a reference to the first element and the length. We will use this kind of slice for all sorts of other collections. We will discuss these collections in detail when we talk about vectors in Chapter 8. Vectors! Cool! We're done with the ownership! We're done with the ownership! Welcome, Dragon! Brain panic, a bit. A bit. I think my brain is currently panicking. The concept of ownership, borrowing, and slices ensure memory safety in Rust programming at the compile time. The Rust language gives you control over your memory usage in the same way as other system programming languages, but having the owner of data automatically clean up the data when the owner goes out of scope means you don't have to write and debug extra code to get this control. Oh, there's a lot of words, what do you say? So we learned about ownership, we learned about borrowing with ampersand, and the slices. And they ensure the memory safety in Rust. And it gives you control to manage your memory, but also helps you to clean up the data when it goes out of scope. So easy to manage, easy to control. Ownership affects how lots of other parts of Rust work, so we'll talk about these concepts further throughout the rest of the book. Let's move on to Chapter 5 and look at grouping pieces of data together in a struct. Okay, I don't think I can conquer struct today. What else do we have? We're going to learn struct, enum and pattern matching, managing growing project with packages, grades, and modules, common collections, arrow handling, generic types, traits, validating, writing automated tests, and finally a big project and functional language closure, cargo, smart pointers, various concurrency. Wait, there's so many more chapters. I can do a whole series reading this book. But that's it for today. I think I need to review the ownership to fully remember what's been covered today. But thank you guys so much for helping me along. If you have questions about Rust, feel free to discuss in my Discord server at signout.com/discord. I think I'm going to continue to stream Rust in like a regular basis because it's fun and I want to like learn some language pretty completely. So maybe like 2 more streams next week. And yeah, on Sunday we're going to have a watch along endurance of White Album 2. Prepare some stomach medicine because it's going to make you painful. The story is gonna be very painful and we are going to watch it. We're going to watch it from the beginning to the end if we can. Alright, thank you guys so much. And see you next time. I get all that? I don't think I get all that. I think for now, yeah, like, I think I understand most of it. But after a few days, it'll be gone, so I need to review. That was a very big chapter, thank you. I can't speedrun Rust. So hard. Alright, see you guys next time. Bye bye. Thank you, Batomi. Thank you, Zoe. What happened to girl wife? I kept her in my cabinet. Phew. Thank you, Mon. See you next time. She was dropped and forgotten. That's a better answer. Thank you. Thank you, like hi. See you next time. Thank you, DVD. Bye bye. Happy bye bye. The World Wife's lifetime ended. Yeah, I'm gonna drop myself once. Died. Thank you, Colopti. Thank you, Landis, Afternoon. Thank you, Alpha Omega. Thank you, Wixie. Thank you, Mr. Lucas. Thank you, Braxon. Thank you, you fun. I'm gonna drop myself. Mic drop. If I do a mic drop, you guys are going to be in trouble. Never drop your wife, okay? Never drop your wife. Thank you, fans. See you next time. See you, Rastasians. Rastasians. Thank you, underscore. See you next time. Bye bye, Kato. This is the sound of your wife dropping. Bye bye.